Hello, welcome to my video about the Red Pitaya Logic Analyzer. I'm John, my amateur radio call sign is N0JPI. So I want to talk about a logic analyzer, what it is, and the different types that there are. So a logic analyzer is really good if you want to analyze digital signals sent from one device to another. Lots of devices use serial buses, and there's different types. We'll look at those later on. And this is really useful for checking what's happening on those communication lines, those buses, and checking it's doing what you want it to do at the time that you expect it to do it. There's two different versions for the Red Pitaya. So there's this one, which is the Pro version. The Pro version comes with an accessory board that provides buffered inputs to the Red Pitaya, and also provides this ribbon cable as well, which has got lots of different connectors. They're just female jumper connectors, and then there's a clip that clips into them so you can connect it to different pins or digital circuits. You can connect this to a standard jumper lead if you want to put the jumper lead in. That works as well. Or you can use these clips. The basic version just includes the ribbon cables and the clips, and doesn't include this buffering board. So it just connects direct into the Red Pitaya's expansion port. The advantage of the Pro version is that it provides a higher frequency. So with the basic version it can sample at up to 3 MHz input frequency, and it can do 50 MHz with the Pro version, and the Pro version also provides buffered inputs which will tolerate voltages from 2.5 up to 5 volts, so you can use it for 5-volt logic like the traditional Arduino, or you can use it for the more modern 3.3 volts, whereas the basic version can only be used on the 3.3 volts. The Pro version does also include this ribbon cable and the clips, and the ribbon cable just connects to the front of the board like that, and then the whole board connects onto the Red Pitaya. This is the documentation website that shows you how to set up your Red Pitaya and includes all the different applications, and this includes the logic analyzer. It shows you the setup, and it also shows you the specifications for the different boards. So it shows you the specification for the Logic Analyzer Basic and the Logic Analyzer Pro. The Logic Analyzer Basic will only work on the STEMLab 125-10. It does not work on the other STEMLabs, although all of the boards can accept the Pro version. If you want to connect the basic logic analyzer, it's just this ribbon cable and some clips. The basic logic analyzer only works on the STEMLab 125-10. It doesn't work on the other boards, and it provides unbuffered inputs. To connect it, it just connects direct onto the expansion header. The black goes to the top, leave the first 3 pins, and then you connect it like that. This won't work on my board because I have the 14-bit STEMLab. Well, it's actually, I bought this Red Pitaya before they were called STEMLab, but it's the equivalent of the 14-bit STEMLab. However, I did buy the Pro version as well, so I bought the board myself, and I bought the logic analyzer myself as well, but STEMLab did actually send me a second logic analyzer, so I have sent me one to test on other boards. When you connect it, it's really important that you line up the header with the pins. It is possible to connect them offline and have them not lined up properly. If you do that, it won't work properly. So it's important that when you look at the pins and you look at the connector and they do line up. It won't damage the board if you do that, but it won't work properly. You have to just pull it off and connect it properly. If you had the aluminium case or another case, then the two would fit together and it would fit flush. But mine hasn't got a case on. Once you've connected the boards together, you just need to connect the ribbon cable. So the black is the ground. So you want it this way. So ground to black. Just push it in. That's it. So then you can connect these to your circuit under test. So I'm going to use a BBC microbit. You can either use these clips, or you can actually just connect it direct. So I'm going to disconnect this clip and just connect into my jumper wire for ground. So the ground is going onto the black one, onto ground on my board, and I've actually got the UART connected to pin 0. So that's going to connect. It doesn't really matter which pin, but because it's the first one, I'm going to use digital in 0. You can use the same procedure whichever version of the logic analyzer you've got, and that's me connected and set up. Now if I wanted to connect other serial bus and digital pins, I can do. So on my setup I've got pin 0 is my UART, my serial, but I do also have an SPI connector which is available, and I have an I2C or I2C connector as well. If we wanted to use one of the clips instead, that's easy. You just push down and you get 2 little connections, and then you can grab over a connection there. That allows you to connect to something while it's already connected. So if you've already got a circuit or you've got something in your breadboard, then that's a good way of connecting without having to disconnect or connect to a circuit that's already been soldered. So I have my Red Pitaya set up with a Logic Analyzer Pro board, and it's already connected to my BBC microbit. To get some signal out of the microbit, I have running this make code application. So it starts off by setting up the I2C, I2C or 2-wide interface setup. It also sets up SPI or SPI, and then shows that it's booted, and then it keeps sending data out. So it sends out I2C data, and then it sets the SPI data, and then it sends the serial data, and it continually does that so it can receive signals. So on the Red Pitaya, you can have a look at the signal with the oscilloscope, but seeing as I've connected the Logic Analyzer, I'm going to use the Logic Analyzer. The advantage of the Logic Analyzer is that you can read up to 8 different digital lines, that the oscilloscope supports 2, and you can decode what's actually going on the serial lines as well. So if I open up the application, now we've got various settings. To begin with, you can just press run and it will look for a signal and produce a result. The problem with this is I haven't set up triggering, so it's not going to give me a useful signal. So if I set my triggering to either rising or falling edge on digital input 0, this is where my UART is set, so this will be the red line, and if I run it now, then I can see my signal. If I zoom out a bit on the time base, I can see the rest of my signal. Now, because there's a circular buffer, it does actually buffer before and after the trigger. So this is data that it's collected, so nothing's happening. And then here's all my data, and then it stops sending, and then just is sending kind of keep alive messages here. So this is my main message. Now, I can set it up with a bit more information than this. So I can go to digital, go to bus, and I can set up my bus here. We've got choices, so we've got I2C, SPI or UART. So I'm sending out data serial UART. I'm going to go with UART. It's on 0. You can set it to receive or transmit, but I'm going to go with receive. And you can set up the baud rate. So this is what my microbit's set to. So I've set it to that. These are the defaults, so I'm going to go with standard. If you wanted to change them, you can change them to all the different options. But in my case, it's a standard. So there is, you can email Red Pitaya, and if you can't decode your signal, they will give you some help. You can download your file that you've detected, and they can help you with that. But in my case, it's fairly straightforward. So make sure the settings are the same as they are for the microbit, whatever's sending you data. That's okay. You can see without actually rerunning it, I have decoded the data. And you've got a choice. You can send it out by hex, or you can send it by ASCII, or you can do various different things. The good thing about this is it does actually show it as you click, it changes. Now, if I zoom in a bit more, I can see the data clearly. So we've got W, H, O, and then A, M, I, colon, and 0. Who am I, colon, 0. And that's what it should be sending. So that's the message. So we've got the basic setup now, but there are more options. So if we go to acquisition, you can change the different options. So because my board isn't really working at a very high speed, my microbit's not a very fast system, so I can just reduce the speed, and if I run it again, if I reduce the sample rates per second, I actually get more samples because it'll do 1 mega samples. That's how much its buffer will save. So if I do 1 mega sample per second, it will save a whole second's worth of data. If I went at the maximum speed, then it would save a lot less of my data. So what can I do now? If we go to UART, you can actually see, as well as on the visual graph, you can actually see a list of all the data. And again, you can use different settings. You can have it ASCII, you can have it binary, you can have it hex, however you want. This one I did find out you had to run it again. So if I wanted binary, press run, and it gives me the data in binary. Or if I wanted decimal, press run again. It's in decimal. Because it's letters, I'm going to keep it in ASCII. Right, now, I've set up a load of different buses. So the next one I'm going to go with is my I2C, I2C 2-wire interface. So this time I look on my board and I've got SDA, that's connected into digital 1. So digital 1 and then digital 2 for SCL. I wasn't sure if it was shifted or unshifted, but I tested it before and shifted seems to work, so I'm going to go with shifted. Now another setting you can do is set up your trigger. So I set it up to trigger on either a rising or a falling edge for the UART, but if I want to look at the I2C, I can change it. So I could change it to digital 1. Now if we run again, this time we should be able to see the I2C data. So this is the data here. It's a lot simpler message because all we're asking it to do is send number 2. So if I go back to data, look at I2C data, and then that's the data there. It's saying as a W, but if I set it to decimal, you can turn off your other buses as well, so you can just see the I2C data if you want. So we've got a clock here, and then this is the message. So we can set up our third protocol, SPI. You can set that up. You just need to know where your master in slave out meso and MOSI master out slave in are set to. So I've set my pins this way. I've left it all as the standard because that's what the microbit sends the data out. And if you needed help, you could email your data and generate an email. They'll be able to help you. Press OK. If I run the system again, I'm going to change the triggering as well. So if I change the trigger and change it to trigger on chip select. So on either chip select, run the system, checks the trigger, it's found it. And if you go to digital and data, you can change the data that you're looking at. So you can look at the UART, we can look at the I2C, we can look at SPI, or we can actually have them all in at the same time and I'll just show all the messages. So these are our data here for the SPI. Let's zoom in a bit. So this is the data that's being sent. So it looks like we're asking for the Who Am I register. That's command 143, and then we're getting the answer back. So that's 143, that's 0 going back as the answer. You can change the data, so I could display it as decimal, as the 143, and there's 0. That might make more sense for this one. And here you can see we've got the clock, we've got chip selected to low when the chip is selected. So I've selected for quite a while on that setup. And so here we've got the data coming out of the master, and then here we've got data coming from the slave, which there isn't any. You have different options as well, so you can return everything back to default. So if you want to change all your decodes, just clear them all, that will clear it back, still get your data. You can have a look at the system information. We don't seem to have any frames per second at the moment, probably it's not running. How much CPU load there is, and memory usage. And you can export it as a graph, and that just shows it to you as a picture. Or you can export it as a CSV file as well, which you can open up in a spreadsheet. So we get those two data. You can adjust the time base. You can scroll around. You can press auto as well, so that auto adjusts the graph. And I think that's everything. I hope you enjoyed this video on the Red Pitaya Logic Analyzer. Don't forget the STEMLab 1, 2, 5, 10 can use the basic or the pro, although the pro is recommended for all the boards. But the basic version won't work on the 14-bit or 16-bit STEMLab boards. If you like my video, please subscribe to my channel, M0JPI, like it, and if you don't like it, then please comment below and I'll see if I can make improvements. Thank you. If you want to know what's inside the Red Pitaya Logic Analyzer board, I've undone the screws. There's just 4 screws on it. It just lifts off once you've taken the screws out. And then there are 2 screws on the inside. It seems to be using the same case as the aluminium case for the Red Pitaya, because it's actually got the heatsink connection on the top. So it must be the same kind of mould, but there's different cutouts. So there's cutouts for the expansion port, and then there's a cutout for where the logic analyzer pins connect. But this heatsink section seems to be the same. The heatsink's not connected to anything on this board. So this is what it looks like on the inside. I'm hoping you can see that. So that's the protection circuit. I'm not an electronics expert, I'm more a software developer, so I won't tell you what all this does because I don't know. That's what it looks like inside, and it's fairly simple to get back together again. Just need to line everything up.